Okay, so let's begin with our new chapter, direct current circuits. Okay, so before that, let me introduce some electrical components. Okay, so first of all, we need to know what is actually the internal resistance. So the internal resistance. So what is actually meant by the internal resistance? So the resistance we actually know, which is certain electronic components that connected to the electric circuits. Okay, so this is the resistance that came from the resistor. Okay, so this time this is actually the internal resistance. So what is actually meant by the internal resistance? So the internal resistance is actually the resistance that lies within a battery. So the resistance within a battery. So it means that internal resistance is actually the resistance that exists inside the battery. Okay, so this is the first electric component that we need to know before entering the topic of direct current circuits. Okay, as for the second, so this one is actually not the electrical component. So this, for the second one, we need to know what is actually the terminal potential difference. Terminal potential difference. Okay, so what is actually the terminal potential difference? So the terminal potential difference is actually the potential difference across the battery. Across the battery, just like so. Okay, so terminal potential difference basically describing the potential difference across the battery. Okay, so for the first statement, we're going to explain what will happen to the terminal potential difference and the internal resistance that occur inside the battery when there is no current flowing through the circuit. That is the first statement. And for the second statement, we're going to talk about what will happen to the internal resistance and the terminal potential difference when there is actually the current flowing through the circuit. Okay, so for the first statement, if there is no current flowing through the circuit, okay, so there is no current flowing through the circuit, flowing through the circuit and the battery, of course, and the battery. Okay, so hence there is no internal resistance inside the battery. Internal resistance inside the battery. So no current flowing through the circuit and the battery, hence the internal resistance inside the battery will not be produced. So this is the first concept. So for the second one, so this is actually the first concept for the first statement, no internal resistance produced. And for the second one, the potential difference. So this is actually called the terminal potential difference, which is the potential difference across the battery. So the terminal potential difference is equal to the electromotive force. So electromotive force, we write it as short, which is called EMF. So the terminal potential difference is equal to the electromotive force. So this is the second concept. When there is no current flowing through the circuits and the battery. Alright, so what will happen to the battery when there is actually current flowing through the circuits? Okay, so when there is current, flowing through the circuits, when there is current flowing through the circuits, the internal resistance okay, so causes the drop in the potential difference inside the battery. So basically, when there is current flowing through the circuit, and hence the internal resistance will be produced, which causes the drop in potential difference inside the circuit. So this actually means that our internal potential difference is less than, so let me use another color. So our internal potential difference is actually less than the electromotive force when there is current flowing through the circuits. Alright, so this is the one of the two important statements that we actually need to know. Okay, so for the direct current circuits. Okay, so let's proceed to our next part. For this part, we're going to discuss about the formula for the electromotive force and the current, and finally the terminal potential difference of the battery. Okay, so let's begin with a diagram of the circuit. So give me a moment. Let me just draw a circuit here. Okay, so this is actually a circuit, and this is actually the resistor, and the resistor is actually connected to a battery. So this is the battery, and this is the internal resistance where lies inside the battery. Okay, so this dotted line is actually indicating the battery. Okay, so this is the direction of the flow of current. Alright, so when the current is actually flowing inside the circuit, okay, so let me just set it up. Okay, so when I is flowing through the circuit, inside the circuit, so if I is flowing inside the circuit, it means that our terminal potential difference basically is less than electromotive force. Okay, so we're going to prove that why this is happening. Okay, so our electromotive force, so first of all, our electromotive force basically is I with the total resistance that included inside the circuit, which is the external resistor and the internal resistor. Okay, so we have the external resistor and the internal resistor. So electromotive force is actually equals to the I multiplied by the total resistor, which is R plus R. So this is basically our electromotive force, which is total up two of the resistance inside the circuit. Okay, so if I move the total resistance to the other side, so what I get for the current basically is the equals to electromotive force divided by R plus R. Okay, so in this circuit, since the electric field is actually shared only for the one resistor, so since we have only one resistor here, hence this is actually our total resistor. So I can conclude that the terminal potential difference, so I write it as PD. So the terminal potential difference of the battery is actually equals to the potential difference. Okay, so across the battery, so this two is actually the same, across the battery, and also equals to potential difference across the external resistor. Since we have only one resistor inside the diagram, so since the terminal potential difference of the battery is equal to the potential difference across the external resistor, so hence I can conclude that my terminal potential difference, which is the total potential difference, okay, so the total potential difference is actually equals to IR. So IR is actually the potential difference for the external resistor, and at the same time it is also equal to the terminal potential difference of the battery. Okay, so if I'm going to sub this equation into this Ohm's law, which is, hence what I get is actually equals to the electromotive force divided by the external resistance added by the internal resistance multiplied by the external resistance. So this is actually, okay, so this P is actually not necessary to be written, and I can also write it as V. So the terminal potential difference of the battery is actually equals to the E divided by R plus R multiplied by R. So this equation proves us that the terminal potential difference across the battery is actually less than the electromotive force. Okay, so this is how we prove it. Alright, so let me see what's next. Okay, so after discussing about the terminal potential difference, so let's look some other I can say as quite important too. So, which is the power loss in the internal resistance. So the power loss for the internal resistance basically is actually equal to the I square R. So this is actually quite different from the power loss that we learned from the previous chapter. So the external resistance basically is equal to the I square R, and this is the capital letter R, which is indicating the external resistance, and this is the small letter r, which is equal to the internal resistance. Okay, so if I go to start this current, which is E divided by R plus R, and this is square, and this is R. Okay, I remain this one as small letter r. Okay, so this is the power loss in the internal resistance. Okay, so for the second one, we're going to discuss about what is the power input for the circuit. So the power input, of course, the power is actually came from the battery. So power of the battery basically is equal to the EI. So normally we write it as VI, which is power is equals to VI, and this V is actually the total potential difference across the circuit, and this same goes to the total potential difference. So the total potential difference initially is actually came from the battery, and hence we write it as electromotive force. So the electromotive force divided by the current. So the current here is actually E divided by the R plus R bracket, and hence what I get for the power input is actually E square divided by R plus R. So this is the second one. And for the third one, okay, so if we have input, of course we also have power output. So the power output basically is actually happening inside the external resistor. So the power output is since it happens in the external resistor, so hence what we need to write is actually I square capital letter R. So this is the capital letter R, and this is the small letter r. So that's the difference, and I hope you can distinguish it clearly. Okay, so I always the same, E divided by R plus R, and this is square, and this is R. So this is power output. Okay, so since we have the both power input and output, and hence we are able to find out the efficiency. So the efficiency basically is equals to the power output, and I write it in short form. So the power output divided by the power input times the 100%. So my power output basically is E divided by R plus R square R, and divided by the power input, So the power input is actually E squared over R plus R. So, and this is 100% of course, and if I move this up, and what I get is R plus R divided by E squared times 100%. So this one can be cancelled, and this one can be cancelled, and finally what I get is actually R over R plus R times 100%. So this is the efficiency that we get. So for the maximum efficiency, basically is only the half, how should I say that? If the efficiency is maximum, the percentage that we actually get is actually only 50%. So maximum efficiency basically is 50%. So if in this condition, the external resistance is actually equal to the internal resistance. So what I get for the R divided by the R plus R times the 100%, so this is 1 over 2, so 1 over 2 times the 100%, so we get 50%. So this is actually the maximum efficiency that occurs. Okay, so if the external resistance is actually less than the internal resistance, or the external resistance is greater than the internal resistance, so the efficiency basically is actually less than the 50%. So that is the one that happened. Okay, so we have done for the power loss and finally the efficiency. Alright, so I think we have done for the first subtopic for this chapter. So let's move on to some exercise. So not exercise actually, this is actually the example that I will show you. Okay, so for the first example, so let's say I have a circuit. So this is the circuit, and this is 12 ohm. Okay, so this is the battery. So this circuit is actually same as the circuit that we discussed just now. So this is actually the series circuit. So this is the battery, and this is the current. Okay, so let's say the external resistance we have, which is I considered as R1, which is 12 ohm. Okay, so the electromotive force given is, okay, so I directly write it inside the diagram, and this is the electromotive force, which is 30 volts, and the internal resistor is 3 ohm. So I write it here as 3 ohm, and the electromotive force is 30 volts. Okay, so for the first question, the question is actually asking for finding the terminal potential difference of the battery. So for the first step, we need to know whether the current is flowing into the inside the circuit. So the answer is yes. there is actually a current inside the circuit, so it means that the terminal potential difference, I can conclude that my terminal potential difference is actually less than the electromotive force. Okay, so since we only have one resistor inside the circuit, so hence the terminal potential difference of the battery is actually equal to the potential difference across the external resistor, okay, which is equals to V is equals to IR based on Ohm's law. Okay, so if you forget always forgotten about the formula for the current, so I suggest you can actually use this formula as a reference. So remember that the electromotive force is always equals to the potential difference across the battery and the potential difference across the external resistors. So if I factorize this I outside, so what I get is actually R plus R. So this is E and this is I equals to the electromotive force divided by R plus R. So what we need to do is actually sub this current inside this formula. So this is E divided by R plus R divided multiplied by R. Okay, so what we need to do is actually sub all the value that is related. So the electromotive force basically is 30 divided by the 3 plus 12 times 12. So if I calculate it, so basically what I get is actually 24 volts. So the 24 volt basically is less than electromotive force, which is 30 volts. So this is the concept. Okay, so for the second question, what is actually the power loss? Okay, so the power loss inside the battery. So we're going to find out what is the power loss inside the battery. So the power loss inside the battery basically is P is equals to the I square R. So I is the E divided by R plus R, and and R basically is the internal resistance. So the internal resistance is 3. So I should remain this one as R first. So we need to sub all the related value inside the formula. So let's see what is the value. So this is 30 and this is 3 plus 12 and square times the internal resistance is 3. So if I calculate it, so finally what I get is actually the 12 watt. So this is W, which is watt. Okay, so that's it for the first questions. So for part A, the question is asking for the terminal potential difference, and for the part B is actually the power loss of the inside the battery. So this is how we find out and calculate the value by using the related formula. And so let's move on to the question 2. So let me just zoom in. So for the question 2, okay, so I have my electromotive force, which is 6 volts, and the internal resistor is equals to 1 ohm. And the diagram basically is in this form. Okay, so let me just draw it again. Okay, so I have my battery, and this is the battery, and I have my first resistor, and I have my second resistor. So basically this circuit is actually in the form of parallel. So this is the parallel, and I consider this as R1 and this is R2. So R1, I have my R1 basically is 3 ohm, and my R2 is 6 ohm. Okay, so for the first questions, find the terminal potential difference. Okay, so there's actually a switch here. So this is actually a switch. Okay, so this switch basically is S1 and this is S2. Alright, so for the question A, find the terminal potential difference when S1 and S2 are open. So since the switch 1 and switch 2, both switch are open, it means that there's actually no current flow inside the circuits. So when there is no current flow inside the circuit, it means that no internal resistance inside the battery. So when no internal resistance inside the battery, hence the terminal potential difference is actually equals to the electromotive force. So the electromotive force is actually the 6 volt. Alright, so this is how we determine the terminal potential difference when both switches are open. And for B, so the condition for B, S1 is closed and S2 is open. So for this concept, when S1 is closed, it means that the current is actually flowing inside the circuits. So when the current flowing inside the circuits, it means that the internal resistance will cause the terminal potential difference of the battery to drop. So my terminal potential difference is basically equals to the voltage across the external resistor, which is V is equal to IR. So my I is the E divided by the R plus R, and R plus R, and this is R1, and this is times R1. So let me see whether I got wrong. So I think it's correct. So my R1 is 3 and my R2 is 6. Okay. So my electromotive force is 6, and the internal resistance, so the internal resistance given here is actually 1 times the resistance 1. The first resistance is actually the 3 times 3. So what I get for the terminal potential difference when the switch 1 is closed and the switch 2 is open is actually 4.5 volts. So this is how we calculate the terminal potential difference. Okay, so for the third question, so this condition is actually when the switch 1 and switch 2 is closed, are closed, sorry, this is actually the plural, are closed. So when the switch 1 and switch 2 are closed, so if we look back to the diagram, so if the switch 1 and switch 2 is closed, it means that the current is going to flow in two ways, which is the direction towards R1 and the direction towards R2. So in this condition, we are going to find out what is the total resistance for the external resistors. Okay, so for the first step, total resistance across external resistor. So in parallel, if the resistor is arranged in parallel, it means that 1 over RT is equals to 1 over R1 plus 1 over R2. So for the first resistor is 3 and the second resistor is 6. So hence I get for the total resistance for the external circuit is actually 2 ohm. Okay, after calculating. Alright, so after combining both resistors, so I can finally find out what is the terminal potential difference for the battery. So the terminal potential difference is actually equals to the potential difference across the external resistors. So hence V, which is the terminal potential difference, is equals to IR. So this I is E divided by the RT, so RT is the total resistance plus the R. So times R times RT, of course. So the the electromotive force is 6, of course. So RT basically is 2 plus 1 multiplied by the total resistance, which is 2. So finally, what I get for the terminal potential difference is 4 volts. So this is how we calculate when both switches are closed. So if the both switches are closed, it means that the resistor is actually more than 1. So when the resistor is more than 1, we need to find out what is the total resistance in for the external resistor. So we need to find out according to the arrangement of all the resistor that included inside this circuit, whether it is arranged in series or parallel. So this is how we find out the total resistance by using the formula of the arrangement in parallel. Alright, so I think we have done for the both examples for the first subtopic. So we are going to discuss the next subtopic in the next video. So So if there any question need to be asked, please comment below this video. So I think we'll stop here now. So thank you. Bye.